In this short video, we're going to talk about compiled versus interpreted programming languages. On this slide, I have collected a small sample of both, and as you can see, most of the early day programming languages were compiled. However, this doesn't mean the future is entirely interpreted, even though the performance gap has narrowed. We'll go into details on why this is the case in just a second. You can see we have modern compiled languages such as Go and Rust, which are gaining massive popularity lately. And in terms of interpreted, you can see that in 1995, the web revolution spawned a lot of tools to kind of allow for the modern web we have today. JavaScript, which at that time was called LiveScript, PHP, which is still widely used nowadays as well. And not to forget Java and Scala, which have basically taken over the world. And Scala being now a very popular language with the functional programming community. Now, let's go over how compiled languages actually work. So I have an example here in C++. I have a hello world being printed in the console. Now with this, what happens is this runs your high-level code, the C++ one you've written, into a low-level code, in this case assembly, and this is done by the compiler, which in this case we can say it's GCC. And what happens after is this low-level code gets translated into machine code, which is the zeros and ones that your CPU actually executes, and it runs your task. What happens in the interpreted case is slightly more interesting. Now, you write your high-level code. What happens is this gets translated into bytecode. And back in the day, this would then be translated into machine code and run. However, the performance was really, really bad. So one thing about compilers is that they're really good at optimization. So nowadays, there is this idea of just-in-time compilation. So what happens is you have your high-level code, gets translated into bytecode, and because the way interpreted languages work is you only compile the chunk that is actually executed, not the entire piece of code, you have a lot of back and forth. So because of this, the chunk you've executed, that bytecode for it gets compiled at that very moment and then gets turned into machine code. That small chunk that gets compiled is heavily optimized. So you get a really, really good performance. So this is why here you now have 4 steps where the just-in-time compilation actually was popularized by Java, and in particular the JVM. This is now a standard feature across almost all interpreted languages, and it has shrunk the performance difference significantly. Now, short comparison, you have compiled languages, and the positives about them are that they're very, very fast because the compiled code is a direct machine instruction and the entire application is compiled ahead of time, meaning you have it already compiled to instructions before you run it instead of while you're running it. So this is called AOT compilation, ahead of time. And then also because you're writing directly to the hardware, it offers lower level access to the machine you want to run your application on. Now, the negatives are that you have to compile for different architectures. So if you want your application to run on an Intel or an AMD processor, like let's say x86, or if you want this to run on an ARM architecture, let's say the new Mac M1, you need to recompile and so forth. So this could be a bit cumbersome. And after every change you make to the code, you have to recompile. Interpreted languages, on the other hand, have one positive, which is that your code is platform independent. The thing is though, that in order to achieve this, you need to have the interpreter installed on the machine. So for example, if we take Python, I can write a Python script and I can run it on an ARM machine. I can run it on an Intel or an AMD machine. I don't have to worry about the architecture as long as I know that they have a Python interpreter built for it. So this solves a significant kind of hurdle to reach your users. And this is the reason why JavaScript is so popular for web, because that interpreter is essentially your browser. You don't have to compile your web page for every possible hardware specification, because you know that the browser exists, it has the interpreter, so your code is just gonna run. And the negatives, however, is that it's slower, right? Because you don't have the instructions ahead of time. You run them as you have an event that triggers that chunk of your code. Now, as I mentioned, because of the just-in-time compilation, that performance difference has shrunk significantly. So it is, instead of 10 times slower, it is marginally slower, right? And if there is a very good example about this, is Java, right? And the JVM. So Java is really, really fast, especially the latest versions. So it definitely shows the premise that interpreted languages do have place in the future, especially now with significantly faster hardware that allows you to just do compilations under milliseconds. And to finish with a small bonus, WebAssembly. WebAssembly is a binary instruction format for a stack-based virtual machine. WASM is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So that's the definition of what WebAssembly, also known as WASM, actually is. It sounds complicated, but the short version is you get to write C++, Rust, or Go, and you get to run this inside a browser, which is usually a JavaScript domain. So this basically allows you to have a compiled language run inside an interpreted environment, which is kind of a big deal. So this is the shiny new toy on the block, and yeah, we should look forward to what this develops into. Okay, that's it. Thanks for listening, and I hope you've enjoyed the short presentation. See you next time.